Well, good evening and welcome. I am Frances Hellman. I'm Dean of Mathematical and Physical Sciences in the College of Letters and Science at UC Berkeley. I'm also a professor of physics. Many of you, our repeat attendees, are probably getting very used to seeing me and my partner in this series, Mike Bochin, the Dean of Biological Sciences. We're both so happy that this series of lectures has found such a wonderful audience. We both like nothing more than sharing great science with our alumni and friends. So I'm very delighted to be here this evening to talk about something that truly captures imaginations, black holes. It's remarkable how much more we know about black holes than we did just 10 years ago. In fact, it's even just 2 years ago. It's such a rapidly moving field. I have to note personally, I was an undergraduate in 1976 and had the opportunity I was doing a reading course on black holes. And at that time, black holes were viewed as a mathematical abstraction. It was a singularity that the math produced, but they couldn't possibly be real. That was just the general view. And then SIG-X1 was discovered. Literally, the first article I ever read was in 1976, a Physics Today article by Kip Thorne on SIG-X1 and how it was showing them to be real. So a lot has happened in the intervening years, of course. And as you know, last fall, the Nobel Prize in Physics was awarded to three scientists for the discovery of the black hole in the middle of our own galaxy, here in the Milky Way. And two of the three scientists who won hailed from the University of California, including our very own Reinhard Genzel, and of course, Andrea Getz at UCLA. I'm going to let Jessica Liu, our moderator this evening, tell you more about why two Nobels were awarded to the University of California scientists, how the findings were made, and I think most remarkably to me, and it makes me just beam to say this, her own role in all of this. Her own role in this discovery, in this amazing discovery. So after that, she will moderate this conversation with three fantastic scientists who are building on the discoveries made about black holes in the past couple of decades and looking forward to new ones. So to say just a little bit more about Jessica, Jessica is an associate professor in the Department of Astronomy. Her interests center around black holes, star and cluster formation, galactic centers, adaptive optics, astronomy, and infrared instrumentation. Jessica leads Jessica leads the Moving Universe Lab here at Berkeley, where they're conducting a search for free floating black holes in the Milky Way using microlensing. Her group also studies how star formation changes in extreme environments in massive young clusters and around the supermassive black hole at the center of our Milky Way galaxy. So over to you, Jessica.
Thank you, Frances. It's such a pleasure for me to play a role in today's event, and I really love hearing about my own colleagues' research, so I think this is going to be a lot of fun. So today we're talking about black holes, one of the most exotic phenomena in the universe, but I wanted to start off with a little bit of an introduction just to put us all on the same page as to what is a black hole. So if I can just share my screen here for a moment, and we will get started with this brief introduction. Oh, yep. And of course, we have to switch again. Okay, hopefully you're all seeing my slides now. Nope. Okay, I hear it's the opposite. I will switch again. Any better now? Okay, excellent. Thank you. Okay, so what is a black hole? A black hole fundamentally is a thing that has its mass and density that is so high that even light can't escape its gravitational pull inside its own event horizon. That's the region at which light can no longer escape. So let's get a little more formal about it. It's when you take all of the mass of an object and pack it into something that has zero volume. That leads to infinite density. And this is what we call a singularity. Anytime you see an infinity in physics, we should always be concerned. It's where our current knowledge of physics breaks down. As a result, these objects truly are at the frontiers of physics and astrophysics. But black holes come in a couple of different flavors. The first is the ordinary black hole. These are 5 to 10 times as massive as our sun. And they're the product of when a very massive star dies, it can sometimes leave behind a black hole. We think that these are ubiquitous and abundant throughout our own galaxy. Something like 100 million to maybe even 1 billion of these seem to be floating around in our galaxy. But this is a theoretical prediction. And these black holes are incredibly hard to find. In fact, less than 20 of them have been found in our galaxy so far, and all of those are very speculative. Another flavor of black hole that you'll be hearing about today is the supermassive black hole. These behemoths are 1,000,000 to 1,000,000,000 times as massive as our own sun, and we think that they reside at the heart of every galaxy based on observations. And you'll be hearing about these kinds of black holes later in our talk from Chung-Pei Ma. Now, these black holes, while we do think they are in every galaxy, they're still challenging to observe. In particular, we can talk about the award-winning discovery of the supermassive black hole in our own galaxy. The center of our galaxy is the closest center we can look towards. So you might think it'd be easy to find the supermassive black hole there, but in fact, it's quite a challenge. The interstellar dust and gas and our own blurry atmosphere get in the way. And thankfully, we can use a technology called laser-guided adaptive optics to correct for that blurring of the Earth's atmosphere. We also use infrared light to probe past the dust and gas and to peer into the heart of the Milky Way. So this adaptive optics technology, what does it do for us? It sharpens up our infrared images and gives us an incredible view of the galactic center. As you can see here, this is the blurry version before we turn on the adaptive optics system. And here's the view of the galactic center once we turn our adaptive optics system on with the Keck telescopes. With these incredibly precise images, we've been tracking and monitoring the positions of stars at the center of the galaxy for the last 20, 25 years now. And some of these stars come as close to the supermassive black hole as the Pluto comes to the sun. They move at incredible speeds, as you'll see in just a moment. And they circle something dark and black and very massive, 4 million times as massive as our sun. And this must be a supermassive black hole. Ooh, and let me see, the movie needs to play. Let's see if we can get that to play. There we go. So as you can see, these are images that we've taken. You can see how the stars are orbiting over time. And this is exactly the measurements that we used to find the black hole residing right at the center. So nowadays, we are using the galactic center as a laboratory for studies of how supermassive black holes interact with their environments. For instance, in 2018, we used a star that was orbiting, coming close, going through its closest approach to the black hole. And we used its incredible speed and its very close proximity to the black hole to test Einstein's theory of general relativity. Don't worry, it still works. So far, Einstein's still the brightest. The Einstein theory of relativity is still the brightest one in the tool shed. We haven't come up with anything better yet. No need for, the data doesn't show us any need for anything better just yet. We're also using these same data sets to look for a swarm of stellar mass black holes that we think might be surrounding the supermassive black hole here. So these black holes truly are stellar ghosts that walk among us. And they are quite remarkable, and there's so many questions we have about them. How many are there, where are they, and how do they influence their environments? Thankfully, we're in a golden age of astronomy, and we humans have invented instruments to study the universe both across the electromagnetic spectrum, that's the spectrum of light, X-rays, ultraviolet light, infrared, and radio waves, including the optical light that our own eyes can see. And we now, in a revolution, have opened a whole new spectrum. This is the spectrum of gravitational waves, ripples in space-time. When two black holes merge, they can produce these ripples in space-time that propagate across the universe and that we now, just in the last decade, have been able to detect. So this whole new spectrum is really leading to a revolution in black hole studies. So I truly think in this next decade, we will make leaps in our understanding of what black holes are and how they belong in the universe. And I'd start off tonight's discussion with some presentations and remarks by Raffaella Margutti on her research in black holes. Let me just exit here. Okay, so while Raffaella is getting her slides set up, I will introduce her. So Raffaella Margutti is an astrophysicist who studies the biggest stellar explosions in the universe, supernovae, gamma ray bursts, black hole mergers and tidal disruption events. She investigates the physics of these events by combining observations across the electromagnetic spectrum. I should also say that Raffaella is our most recent recruit to the astronomy department here at UC Berkeley. In fact, she's not even here yet. She'll be arriving on July 1st, and she's now finishing her last semester at Northwestern University in Chicago on the faculty there. So we're incredibly happy to have Raffaella join us and tell us about her research. Raffaella, take it away.
Thank you, Jessica. I hope you can see my slides. All right. Yeah, I am truly excited to be here today. And I guess we start from the beginning. We start by talking about how do we form the smaller size black holes, those that have mass of 1 solar mass or so. And to do that, we'll have to talk about cows. And so here's the reason. So there was just a joke to start. So in the world of transient astrophysics, we call every new thing that appears in the sky with the name of the year. In this case was 2018. And then we're not very creative. We start with AAA, AAB, and so on. And this poor thing just happened to be a stellar explosion that happened in July 2018. And it just happened to be COW, but it became soon the cow for everybody. And you can see actually the light that this transient was producing. So the cow is a very peculiar stellar explosion, and it is so special that to study this explosion in the sky, we have actually triggered a number of observational facilities, and you can see that we used a fleet of spacecraft from NASA and ESA. We used a whole bunch of optical telescopes. You can see your beautiful Keck telescope right there, as well as a bunch of radio antennae. And the reason is that we really wanted to build a panchromatic view of this stellar explosion. Something very, very, very special was happening in the sky in that particular location, and we really needed all of these eyes to stare at that part of the universe. So why? Let me give you the punchline. So what you're looking at there is one of my favorite images, is the first image in the hard X-rays, so very, very hard radiation that has been captured of a stellar explosion that is not in the Milky Way. And what we could understand through by putting together photons across the spectrum is that this explosion was very asymmetrical, and that this explosion was running through a very rich environment. And I'm sure that by now, you might be puzzled and even thinking, why on earth is she here telling about this? Why is that relevant? Well, in one sentence, the reason why this is relevant is because these photons that you can see there are actually coming most likely from the birth of a black hole. But to truly appreciate that, let me take a step back and get you through what I call the ocean of ignorance of my field, good ignorance that fuels research. So we do know, as Jessica was telling us, that massive stars, they explode, they run out of fuel, the beautiful hydrogen, they implode because of their own gravity. And theory tells us that what is left behind after this beautiful gigantic explosion is either a neutron star or black hole. However, I had to put there that big question mark, because as of right now, there is no way, nobody on this planet can tell you which type of neutron star, which type of black hole do we form? Do we even form a neutron star or black hole? We truly do not know. And the cow, the observations of the cow actually allowed us to make a little step towards answering this question. So as an observer, I always look at what we can see with our eyes and not necessarily trust theorists. And we do know that theorists are at least partially right when they tell us that explosions of massive stars produce neutron stars. We do know that because if we look at the beautiful Crab Nebula in our own galaxy, what we're looking at is what is left behind of a stellar explosion that happened 1,000 years ago. And we can actually look at the little dot, that white dot right there. That's a beautiful neutron star that was formed by this explosion. However, we can't play the same game with other stellar explosions that happen outside the Milky Way. And the reason is pretty simple. The reason is that the light that we see from these explosions is actually coming from a very thin crust around the object. So we have no way to see the inside of this star that just died. And our only hope is to wait to wait for this ejected material to become transparent. And at some point, the photons produced by this potential neutron star or black hole that we formed are able to actually reach the observer, are able to reach us. This is exactly what happened, what is happening right now for the Crab Nebula. So we had to wait for 1,000 years. However, I'm pretty sure that some of you might be thinking that, what if I start off with less mass? So maybe my star had less mass around. And even better, what if that mass was not spherical, but it was very, very highly asymmetric? That would actually give us the opportunity for these photos to actually leak out much earlier in time. This means that we would have the opportunity to see some of the photons produced by a black hole or a neutron star that is just born, like literally just born. This is exactly what happened for the 18 Cow event. We think we could see evidence for formation of a compact object in real time for the first time. So let me try to guide you through how we came to that conclusion. And I promise this is the only plot that I'm gonna show. What you have there is brightness on the y-axis versus energy of the photons on the x-axis. And I want you to realize right away that we had to use not one, not two, but 4 spacecraft to put together these observations that you're looking at. And in this plot, there are different components. The one thing I would like you to bring home is that this blue line that you see that I'm emphasizing right now, this is how transients look like in this phase space. But I'm pretty sure that you are realizing that here we have 2 other things happening. We have that little hump. I can tell you this is iron emission that we're seeing. And then there is that bigger hump that we call Compton hump. This is something that we have never ever seen in any other stellar explosion that the Cow showed. And this is actually the reason why we thought that a black hole was formed. Let me try to give you a sort of a heuristic understanding of why that is most likely true. In astrophysics, anytime we do not understand much of what is going on, we just turn into our backyard and try to learn from what we know. And in our own galaxy, when we have black holes that are little black holes that are accreting matter, the way they look like in the spectrum is like this. Let me emphasize again, one feature is this little hump is iron emission, and this is the other bigger feature that we connect to these accreting black holes, the Compton hump. So now maybe I managed to convince you that maybe it's not so crazy what I'm saying, that the features that we saw in the Cow were actually very typical, very similar to those that we associate to accreting black holes. So maybe the Cow really formed a black hole and we could see it a few days after formation. So I want to end with one point that is very close to my heart, which is the true value of panchromatic observations across the entire spectrum. We really need to acquire and document every single photon that our universe produces, because every little photon is telling us a different piece of the same story. This is, in my mind, the very first step towards what is now reality in the world of multi-messenger astrophysics, where we combine photons and gravitational waves. With my team, we played a big role in the characterization of the first and only event for which we do have light and gravitational waves detected. This was a neutron star merger, not black holes, but neutron stars. And I'm very excited to share with you tonight that at Berkeley, we're putting together, creating a completely new time domain survey that is called Lassie-Schmidt Siren Survey, LS4 in short. That is going to play a huge role in this new world of multi-messenger astrophysics. And that's all I wanted to share with you tonight. Thank you so much. And I can
Thank you, Raffaella. That was fantastic. So if you have questions for Raffaella about her exploding births of black holes, please enter them in the chat right now. And while we're waiting for a few questions to come in, I thought, Raffaella, I'd ask you for one or two in particular. Now that there are so many explosions in the sky that we can see, how do you know which ones are going to be interesting?
That's a great question. We have thousands and thousands of explosions every night, believe it or not. And the way we actually decide how to get on target and when is by using artificial intelligence, so machine learning algorithms. So we need the help of machines to actually go through the haystack and find the needle.
We had a question from someone in the audience who was asking, in your figure, what was the data shown in the dotted blue lines? You can always
Great
share
question.
it back again if you'd like. Yeah.
Yeah, sure. Let me do it. So the reason why I said that this was typical of all stellar explosions is because this is radiation that is coming from the shock that the stellar explosion launched into the environment, that accelerates particles and creates very, very high energy emission. In space, it's almost impossible to avoid shocks, and stellar explosions are great engines to produce those shocks. So it's ubiquitous.
We had another question from the audience that I'll expound on a little bit here. Can you tell us a little bit about how gravitational waves, what they are, and also how they're affecting your research?
Yeah, that's another great question. So one part of the science that I do is actually trying to locate the electromagnetic counterparts of whatever produces gravitational waves. And right now, that is either merger of two neutron stars or mergers of a black hole and neutron star or black hole. And what I am trying is to actually localize them and characterize them. So understanding how much mass was produced, what was that mass made of, how much energy was produced.
Great. So I think it's definitely true that while gravitational waves are one probe, it's just as important to get those electromagnetic waves if we can as well.
Correct.
We had another question about the iron. Where does the iron come from?
That's a great question. So I've been asked many times. So this primordial iron, so it's not iron formed by the explosion. It's just too early for that. And it's just that it was the inside the star. It was the ejecta of the star. Yeah.
Excellent. We had another question. Does the data suggest that the neutron star black hole forms in days after the stellar explosion, even sooner than that, later than that?
It's way earlier than that. So at least I would say that data can't actually tell us the answer right now. And this is where we would really love to have gravitational waves detections of stellar explosions, because they can probe this process of collapse. According to theory, the collapse is like how the entire explosion gets started. And then a shock propagates through over, let's say, depends on what type of star, let's say minutes, and then the explosion in photons that we know of starts for real.
Okay, and then we have one last question that we can take. Why is the mass so important, the mass involved in the explosion? Why does that matter so much for whether something becomes a black hole or a neutron star?
That's also a great question. So when I was a grad student, I would say that we thought that more massive stars would give origin to black holes and the smaller part would give origin to neutron stars. This has been challenged recently, and there seems to be islands of black holes formation along the mass spectrum. So I would say we do not know the reason.
Yeah, and I'd say that's a big change in our picture just in the last few years. We used to think it was really one side and the other, black holes and neutron stars, not so much anymore. All right, keep typing in your questions. We'll be responding to them in the chat along the way, but thank you so much, Raffaella, and we're going to move on to our next speaker. And again, we'll have room and time at the end for additional questions. So next up, we have Michael Medford, who's currently a 6th-year graduate student pursuing his PhD in astrophysics. He searches for black holes in the Milky Way using large imaging surveys, and he develops innovative techniques for finding these black hole needles in the all-sky haystack, so to speak. He works jointly with Peter Nugent at Lawrence Berkeley National Laboratory and with myself in the Department of Astronomy. And Michael, while you're sharing your screen, can you tell us a little bit about your research and the project that you're currently working on? And go ahead.
Thank you. Thank you so much, Jessica, for the introduction. So I've been, as Jessica said, I'm a 6th-year graduate student here at UC Berkeley. And over that time, I've worked on a number of projects, including trying to find Kuiper belt objects, to cleaning up atmospheric disturbances, to long wavelength optical images. And my work with Jessica is centered around trying to find black holes in the Milky Way. And this is what I'll be talking about today. So these are the stellar mass black holes, the ones that are about the mass of our sun. And I'm going to talk a little bit about how we find them. Now, when it comes to black holes, there are often more questions than there are answers. And these questions span a whole range from where are the black holes and how did they get formed and what do they tell us about our galaxy? But probably the biggest puzzle is just, where are they? As Jessica alluded to, models predict anywhere from hundreds of millions to billions of black holes in our Milky Way, and yet they turn out to be quite difficult to find. And these are for reasons not just because they don't emit any light, but because relatively speaking to the number of stars in the Milky Way, they're actually quite rare. How we find these black holes are determined by where we think they are and how they formed. The different formation scenarios for black holes motivate different methods of detection because they give off different kinds of signals that require different instruments. One type of black holes that we've become able to find quite commonly are stellar black hole binaries. These are pairs of stars where one of the two stars undergoes the transformations that Raffaella was describing in studies and becomes an X-ray emitter. As it gobbles up the matter of the nearby star, the black hole tears apart the hydrogen and helium into really bright X-ray emissions. We've used this technique to discover dozens of black holes since the 1970s, including Cygnus X1 that Dean Hellman was talking about earlier. I would put this detection method in the tried and true category, and the way that we found most of the black holes in our own galaxy to date. The next type of black hole that we've just figured out how to detect are binaries of black holes with each other. These have been hitting the news a lot recently, and they're detected through gravitational waves. The Laser Interferometer Gravitational Wave Observatory, or LIGO, measures the distances between mirrors to detect the tiny ripples in space-time caused by black holes as they rip each other apart and form more massive black holes. This technique has found tens of black holes since 2015, and to its credit, I'd categorize this as yesterday's cutting edge. We're now getting so many black holes, we're actually starting to be able to do population studies using this method. What you'll notice in common with both of these populations is that they're binaries. They're stars that come together in pairs. But we know that most stars in the Milky Way are isolated, they're on their own. And this presents a challenge because isolated black holes do not emit any light of their own. For this, we at Berkeley are innovating a new technique, or rather an old technique for a new purpose called microlensing. And here at the Moving Universe Lab, Jessica Liu and myself and other members of the lab try and use this technique that I'll describe a little bit more to try and find background light that gets bent by black holes. No detection so far, but this is today's cutting edge and where we hope to be making detections soon. So what is microlensing? Microlensing is yet another phenomenon that is predicted by Einstein's theory of general relativity. As massive objects move throughout space, they bend and warp the fabric of space-time, acting like a lens, and in this case, like a magnifying glass. As black holes or stars pass throughout the Milky Way galaxy, they bend space-time and the light behind them. So if we get lucky, if a background star happens to be passed in front of by a black hole or other massive object, that light is bent just like a magnifying glass can bend the light of the sun to create a bright spot on a piece of paper. This presents a temporary brightening of the background star and dimming that we call photometric microlensing. Now, this isn't just theory. Since the mid-1990s, we've discovered thousands of these objects with this same kind of signal, a characteristic brightening and dimming. And yet, all of the detections of microlensing we found to date have been stars lensed not by black holes, but by other stars. And the work that we're doing is to pioneer this technique for the detection of black holes. Now, to do this, you need a lot of detections because black holes are relatively rare compared to stars. And so we turn to large sky surveys that will generate lots of microlensing candidates. My own work centers around the Zwicky Transient Facility. The Zwicky Transient Facility, or ZTF for short, is a massive 47 square degree camera that photographs the entire night sky every 2 to 3 nights in multiple colors. I have here on the screen the footprint of ZTF posed on top of the Andromeda Galaxy and next to the moon, and alongside some other telescopes you might be familiar with, like the Hubble Space Telescope on the top left. And you can see that ZTF dwarfs it in size. This allows us to keep an eye on many more stars every single night for those microlensing candidates. A recent paper that Jessica and I published ran simulations of the ZTF survey, and were able to make predictions for the number of microlensing events that we expect ZTF to find. Along with the characteristics of the ZTF telescope and in-house microlensing simulations that we've constructed, we predict that the ZTF telescope can discover nearly 1,800 microlensing events in its first 5 years of operation. This would be the first time we can detect microlensing events outside of the galactic center, and this should be one of the instruments that provides us a large catalog of black hole candidates that we can follow up with higher resolution follow-up. Unfortunately, the microlensing signal from a photometric detection isn't enough, and so that's why we need further instruments to turn these candidates into black hole detections. But first, let's talk a little bit more about how you make a microlensing detection from these pieces of the puzzle. The first piece that we have are our ZTF observations. This is the data that comes in from the telescope on a nightly basis in multiple colors. Next, we combine that data with microlensing simulations that we've built in-house to predict these events, led by Casey Lamb, another graduate student in the Moving Universe Lab. Then my work centers around leveraging the computational resources at the Lawrence Berkeley National Laboratory, where the NERSC supercomputers allow us to process this amount of data at scale. Millions of observations are taken per night, and we process them through Puzzle, the pipeline utility for ZTF lensing events. This software stack gives us hundreds or thousands of candidates that we can follow up with more high-resolution instruments to turn them into black hole detections. Now, why do we have to do that? Well, it turns out that when you make a microlensing detection, it's hard to know whether you're making a detection of a really massive object that's close or a really low mass object that's far away. And we have to make another measurement to break what we call this degeneracy. To do that, we use instruments like the Keck telescopes. As Jessica talked about earlier, adaptive optics on the Keck telescopes allows us to make measurements of the motions of stars hundreds of times more precise than the resolution of the telescope. Now, why is this relevant to microlensing? Because during a microlensing event, not only is the background star amplified in its brightness, but it also appears to move ever so slightly. You can see an animation here on the right where the lens is passing by in front of us in yellow, and the background star is being warped into two images in blue. The average of the location of those two multiple images is this red dot, and you can see it shifting ever so slightly left and right. That tiny shift allows us to break this mass distance degeneracy and get a mass measurement of the lens. We can take that mass measurement along with information about its brightness to convince ourselves that our candidate is indeed a black hole. We then can run our own simulations and compare that motion of the source and lens to what we predict from our models. And these models can predict for us certain regions of parameter space where you get certain characteristics of brightness and certain characteristics of motion where only black holes would be present. You can see here in a plot on the right where this change in brightness on the y-axis is compared to the motion of the source and lens on the x-axis. And the different dots represent our different objects in our simulation. And the contours in blue drawn on top are our candidates that we're currently following up. And you can see we have a few promising candidates that may very well fall in the black hole region of those black dots. We are on the cusp of a revolution. Today, we can generate candidates hundreds at a time from telescopes like Ogle and MOA, and follow up those candidates with the Keck telescopes and adaptive optics. Very soon around the corner, we will be able to generate tens of thousands of candidates with instruments like the Roman Space Telescope and the Rubin Observatory and LS4, as Raffaella was describing earlier. And with our new generation of instruments, we'll be able to follow up these tens of thousands of candidates to create hundreds of black hole detections using the 30-meter telescope, the Roman Space Telescope, the James Webb Space Telescope, and let's not forget the Keck telescopes as well. It's a very exciting time to be hunting for black holes. And I don't think we're done yet in revolutionizing our understanding of our own galaxy through these detections. So with that, I'd be happy to take any questions that you have about how we go about finding these black holes in the Milky Way galaxy.
Thank you, Michael, very much. Again, a reminder, please do post your questions in the chat and we'll field them for Michael. So Michael, let's start off. How does the presence of so many new black holes that we're finding impact the ratio of dark matter to baryonic matter in the universe, or is it still a relatively small amount of mass overall?
This is a very interesting question. So the question of where dark matter comes from, this missing mass that we see gravitationally pulling things in the universe, but without emitting light, is a really open question. There are people looking for dark matter in very tiny particles, and some people in very massive ones. Some of the work that we do actually contributes to a pretty exotic theory of dark matter that says it's actually caused by black holes that could be born either from the birth of dying stars or even primordial black holes made just after the Big Bang at the beginning of the universe. So the discovery of black holes may give us some different answers as to where dark matter comes from.
We had another question here. Where and how far away is the closest black hole?
That's a good question. So the closest black hole that we can all agree on and be confirmed exists is the one at the center of our own galaxy. So that one would be it's about 7,000 parsecs away, or a parsec is about the distance to the nearest star. Now, if it is true that stellar mass black holes that stars turn into stellar mass black holes, and we can use techniques like microlensing to detect them, we may be able to find black holes that are much, much closer than the center of our own galaxy. But rest assured, they won't present any danger to us. They're not like vacuum cleaners that are going to suck us up. We'll be safe and okay, but they might be much closer than we now think.
And speaking of sucking up matter, we had a question about, does dark matter fall into black holes just like normal matter? And does it emit anything if it does?
Well, certainly if dark matter's around a black hole, it's going to be gravitationally attracted. So it's going to be sucked in just the same way. But unfortunately, we don't anticipate it to emit any light unless there's some really exotic physics, which could be the case. Black holes are pretty exotic places. We don't anticipate them to emit any light. Okay,
and then we had one last question that I wanted to pass on to you, which is, what is the easiest way to find a black hole? I don't think any of them are particularly easy, but yeah, maybe one of the tried and true that you mentioned in the beginning.
Sure. So finding X-ray binaries, where for finding stellar mass black holes, X-ray binaries are the way that we found dozens of different black holes. So this is where a black hole is next to a star and it's gobbling up the mass of that star. And when it's ripping apart those hydrogen and helium clouds, it emits these very bright X-rays. So to the best of our knowledge, that so far is the easiest way, so to speak, to detect black holes.
All right, keep your questions coming and Michael will do his best to answer them in the chat as we continue. Thank you so much again, Michael. Next up in our conversation, we have Chung-Pei Ma, who's the Judy Chandler Webb Professor in Physical Sciences and a Professor of Astronomy and Physics. I'm very pleased to have her here, my colleague from the department. Her research interests center around theoretical cosmology and astrophysics, and she uses both observations and supercomputer simulations to study dark matter and dark energy, the cosmic microwave background, galaxies, and their supermassive black holes. So Chung-Pei, welcome. And as you're getting your slides started, could you tell us a little bit about your research?
Yes, I was trying to unmute myself.
No problem.
Okay, can you see the slides now?
Excellent. Yep, thank you.
Okay, so I would like to go a bit larger in scale, and especially in mass scale, and go back to the black holes that Jessica was talking about, the supermassive black holes, and to talk a little bit about what we know about these black holes in galaxies other than our own, the Milky Way. And so just to recap, Jessica and her advisor, Andrea Ghez, and our own Reinhard Genzel made this incredible measurement of the black hole at the center of our own galaxy. And I want to highlight this decimal points that they were able to get 4.152 million suns for the mass of this black hole. It's beautiful measurements as you saw those individual stellar orbits. But we don't have such a luxury for other supermassive black holes since they're way further. And therefore we can only use integrated light. We cannot resolve individual stars like the way Jessica was able to. And as she said, now we believe that every galaxy has a supermassive black hole at its center. So now I would like to talk about, there's a bigger supermassive black hole that we have known for since the 70s. And this is 2,000 times more distant, 1,500 times more massive, at 6.5 billion now suns. And this is at the center of the giant elliptical galaxy M87. And some of you may have seen the first black hole image that was taken in 2019, and that was made for this black hole. So for several decades now, we have known that bigger black holes seem to live in bigger galaxies. So we have this correlation, and this tells us a lot about the symbiotic relation between black holes and their host galaxies, how they impact each other, how they survive together, how they feed on each other. And this is a very active field of research right now. How do black holes impact galaxy formation? And here I'm just showing sort of how the Milky Way black hole is at the very low end of the spectrum, mass spectrum at 4 million. And M87 is, for 34 years, was at the highest end at 6 billion, was the largest known black hole in the local universe. So one natural question to ask is, there are bigger galaxies than M87, so are there bigger black holes? And that's what we have been able to explore in the last decade here in Berkeley with my research team, that we were able to find black holes beyond the M87, 6 billion, to open up this new parameter space and find a population of ultra-massive black holes. And one of the projects we're doing right now is to systematically study the 100 most massive galaxies in the local volume and to study the black holes at their centers to understand this population better. And here I would like to just highlight two black holes that we were able to find that broke the M87 record. And as you can see here now, that they are at about 3 times even more massive at 17 to 20 billion suns. And this is bigger than some little galaxies as a whole, right? So obviously these black holes live in ginormous galaxies themselves. And I want to highlight here is on the right one, this NGC 4089 was the first one that we reported in 2011 that went beyond M87. And this is a sort of an obvious place to look. The hard part to do was to get the observational data to actually detect the black hole and weigh it. And the reason this is an obvious place to look is because NGC 4089 is a very, very massive galaxy. And this galaxy itself lives in a very massive cluster of galaxies, a society of galaxies called the Coma cluster. So it's like the Manhattan of the universe. And if you want to look for skyscrapers, you will go to Manhattans of the universe to look for the biggest black hole, the skyscraper. So we found that. Now, in 2016, we reported the discovery of another ultramassive black hole at a very comparable mass. And this was in a lesser known galaxy called NGC 1600. And the reason this was a little bit more surprising, and we're still studying this, this demographics, is because NGC 1600, although it's a very massive galaxy itself, it kind of lives in the Midwest town in the US. So it's a group of galaxies, but it's nothing as spectacular as the Coma cluster. So why do we find a skyscraper in a little sort of mid-sized town is currently a puzzle. Who has been feeding this black hole to make it as massive as a black hole in Coma? And so a lot of numerical simulations are being done to understand the different environments of these massive black holes. And here I'm just highlighting 2 of the several we're beginning to uncover. And to make these discoveries, we rely on the most powerful telescopes and computers available to us. And luckily here at UC, we have we're privileged to have access to the Keck telescopes. So we're using some of the most advanced spectrographs there so that we can pierce towards the center of each galaxy and measure collectively what the stars are doing, and using the stellar velocities to measure the gravitational pull due to a central object, the black hole. And we also need supercomputer clusters to model the stellar orbits in a very extensive way in order to tease out the black hole mass. Now, in addition to these facilities, well, of course, we need brains. And here I would like to highlight some of the students who have gone through my group. And Melanie graduated a couple of years ago, and she's in the data science, working in data science company in the Bay Area. And two current graduate students, Matthew and Chris, they're working very hard right now as I speak. We have Keck proposals due tomorrow, actually. And also, I want to highlight Jen Ito. She was an undergrad here, and she's now a physics graduate student at UC San Diego. And currently, Shauna Modak, who is a senior here at Berkeley in math and physics. And I think he's on track to graduate at the top of his class. And just a few days ago, we had a Zoom session. He was asking me about graduate school choices. Among the many he can go to, he's asking me whether he should go to Princeton, Harvard, or Yale. I say, wow, those are pretty good choices you can make. And he's also our LNS SURF scholar that funded his research last summer. He won this award. Okay, and here I want to leave just with some of the big questions we are asking, and the reason these massive, very supermassive black holes, ultramassive black holes are important. There are various reasons. One is it tells us how galaxies and black holes get to this size, the assembly history of these objects, because the most massive things carry, in some ways, the most historical baggage and information of the past history of the universe. So studying them will allow us to get a glimpse of how the past history, how the universe evolved. And how many are there, the number density, and where are they, as I mentioned, the environment, and their symbiotic relations with their host galaxies. And just to tie back to what we heard earlier about the stellar mass black holes and LIGO's discovery of the gravitational waves, that binary black holes also evolved, can also form, supermassive black holes can also form binaries. And when they coalesce, they will also give out gravitational waves, but they're at a much lower frequencies. And we are all rapidly urgently looking for these wave forms. Okay, and just very last 30 seconds, I just want to highlight that science is very interdisciplinary in the sense that even though we're looking for black holes, along the way, we actually need to measure distances to these black holes. So we have at a site, sort of a parallel program measuring distances to these massive galaxies. And because we have distances now through the so-called surface brightness fluctuation method, we have velocities. We can actually measure the expansion rate of the universe. So just in today's, the Berkeley if you're on the website, or you can go to the website or our email chain, Bob Sanders had an article featuring our latest measurement of the H0, the Hubble constant. And this is, I spent a lot of time trying to edit this plot. And it shows the disconcordance right now between the late time measurements and early time measurements. Maybe this will be a good topic for the one of the next conference we'll have. Thank you.
Thank you so much, Chung-Pei. So we have a few questions for you. One right off the bat, do black holes theoretically expand or lose energy and die out? And we had an earlier question about black holes evaporating. Could you say a little bit about what happens to black holes over time?
Right, so the Hawking radiation definitely is a way to make them shrink, evaporate. The time scale for Hawking radiation for these astrophysical black holes we're talking about today are the time scales are longer than the age of the universe. So they are not really relevant for our type of black holes. They are very relevant for tiny, tiny black holes that lived in the early universe. So the way black holes, as we know, that evolve is by gaining weight, gaining mass. They accrete and they grow in mass.
Great. So why is it that we think that every galaxy has a black hole? And is it really a supermassive black hole, at least? Why is it really always at the center?
Yes, we wonder about that too. So we don't know if it's always at the center. That, in other words, to say that there may be black holes that have been kicked out from the center, and we just don't quite know where to look. It's very hard to look unless you know where to look. So in some ways, we always look at the center right now. And so far, if we look hard enough and we get good enough data, we always get a measurement. So we haven't found a galaxy for which we have very stringent upper limit on the black hole mass.
So we've talked a lot about stellar mass black holes and supermassive black holes, but getting from one of these small 5 solar mass black holes up to these billion solar mass black holes, that's a big leap. So how do these supermassive black holes form, or is there a link between the two types?
Absolutely. We're also wondering about that. That's a very active field of research. There's sort of a missing gap right now between, in the sort of thousands to 10 to the 500,000 range that we have not been able to find one of these so-called intermediate mass black holes. We do think they should exist at the center of maybe stellar clusters or tiny galaxies, but that just happened to be a very awkward place for current observational facilities to resolve. So either so there are two scenarios. Either these black holes that Raf and Michael are looking for, they are the initial seeds, and maybe they collapse together, start stellar clusters, and they migrate to the centers of galaxies and feed to the billion solar mass black holes we're seeing. Another scenario is you get a primordial cloud, of 100,000 solar masses itself and direct collapsing into a 100,000 solar mass black hole. People are debating and people are looking for observational evidences for either. So far, it has been very difficult to refute or confirm.
Maybe a question for the next generation of telescopes and observatories. Great, so I'd like to encourage everyone to open up your questions for all of our panelists today, and include questions about not only black holes, but also what it's like to study them. So I thought I would turn a quick question to Raffaella, who's our newest member. Why are you coming to Berkeley, and what is it about, what is it that makes Berkeley an exciting place to study black holes?
Yeah, so the short answer is to play this game of multi-messenger astrophysics at the highest possible level. And I say that because of two ingredients. One is I'm very much looking forward to an extremely stimulating intellectual environment. Second ingredient, it's paradise for observers, is the land of telescopes.
Yes, we're very privileged to have access to the Keck Observatory in Hawaii. Those two twin telescopes are incredibly powerful for the study of black holes, as you've heard today. So Chung-Pei, you showed us very nicely your students that you've been working with. What is the importance of students, both undergraduate and graduate students, in your research pursuits overall in the study of black holes? What role do they play?
Critical. I mean, without them, I would not be here today. And it's the great minds, brains that Berkeley is able to attract here, both at the undergraduate level and the PhD level, it's just vibrant. I'm having so many Zoom sessions with them, and the young minds are incredible. They're so much better than I am at programming and at remembering anything. I rely heavily on them, and they are just great to work with. They energize me, they keep me young. Excellent.
Yeah, I 100% agree. Speaking of programming whizzes, Michael, in your role as a graduate student here, how has Berkeley given you the tools, not just to study black holes, the universe as a whole, but those tools that will go beyond graduate school?
Well, it's kind of unfair because my answers were just stolen by these two answers, because it's basically the same things that attract a graduate student are what are attractive for faculty members. It's the brilliant minds that are going on, the collaborative environment, the ways that people are always trying to branch over into new disciplines and kind of help cross-pollinate the different intellectual fields that are here. For me personally, the access to the resources, both observationally, computationally, the Savio Compute Cluster, the partnerships with the Lawrence Berkeley National Laboratory and the supercomputers there have so enhanced and supercharged the work that I can do that it's given me the skill set to be able to, take large, complicated computational problems and, like you were saying, find the needle in the haystack, right? Take these, so many problems that we're working on in society today are about processing large amounts of data and trying to create actionable insights from that data. And astrophysics is a great place to learn how to do that because we've got a lot of questions to solve and fortunately a lot of data these days.
Excellent. We just had a question here that said it's an exciting time for astronomy, and all these incredible new instruments are becoming available, both for the electromagnetic and the gravitational wave spectrum. What is the central thrust of black hole research going forward? I think you've seen a little bit of it in each of the talks here, but maybe each of you could take a moment. What do you think is the big question you're looking forward to addressing in the next decade? Let's start in order. Go ahead, Raf.
Yeah, so I tell you my dream. The dream would be for me to be able to say, this star, I can tell you, is going to blow up and produce this black hole with these properties. That's the dream.
Michael?
I would say leveraging these new generations of telescopes to make seamless pipelines for triggering follow-up, just taking the fire hose of data that we have and being able to seamlessly go. I mean, it was, 25 years ago that we were observing things on glass plates. So, the transition from there to here, I'd love to see the field go to a place where a scientist doesn't have to get involved until you've got all the way down to the candidate stage. And I think that's a possibility for us.
Chung-Pei?
Yeah, the very massive black holes we're finding, they are hotspots for producing these gravitational waves I talked about if they're in binaries, because the more massive they are, the closer they are, the stronger the signals will be. So LIGO had opened up this new window of new forms of radiation, right? Gravitational waves, but their frequency is they have only heard the piccolo of the orchestra as the very highest frequency. And I'm dying to hear the bass and the beautiful cello of the universe.
And I'm very excited for the day when we have as many small black holes as we have large black holes. It seems backwards since those large black holes are so far away and these small ones are so close to home, yet they're very challenging to find. So that's what I'm looking forward to, the next horizon. Okay, I think we have time. Actually, I think we are out of time for questions, unfortunately, but we have just a couple more minutes and I want to bring it back to Dean Francis Hellman. So we can continue answering questions in the chat, and we will for the next couple of minutes. But I wanted to remind you that Dean Hellman's a professor of physics in condensed matter experimental physics in particular, and she studies the thermodynamic properties of novel solid materials and thin film semiconductors and superconducting and magnetic materials. She's also recently the president-elect of the American Physical Society and a member of the Academy of Arts and Sciences. And we astronomers and astrophysicists are particularly interested in some of her current research, as it exemplifies the importance of basic science. She's a member of the LIGO team working on the next generational gravitational wave detectors that you heard a little bit about today. And she's inventing new materials to coat LIGO's mirrors in order to better detect those ripples in space-time I talked about. So quite possibly she's helping us make future discoveries about black holes. Francis, I'll turn it back to you. Oh, Francis, you're muted.
Yep, there we go.
There we go.
So yes, it's I was actually first of all, let me say thank you, Jessica. That was I loved hearing your stories. I loved seeing your work, getting to hear more about your work. And thank you, Chung-Pei and Raffaella and Michael, for sharing with us your work, a glimpse into where black hole research is going. And I was going to make a closing comment about it's been very exciting for me as a condensed matter person to have gotten involved with LIGO, and particularly novel and interesting to have gotten to meet Kip Thorne, who I read about when I was an undergraduate, and now working with him, which is, it's always remarkable to discover things like that. So I was going to make that comment, But I found that the comment I actually want to make here is how much more exciting it is to be here at Berkeley and to have the privilege of working with the people you've just heard from. So although it is, of course, a great privilege to have gotten to meet Kip Thorne, who was a hero of mine in college, but I feel even more privileged to have, I just met Raffaella just on this Zoom call. I literally, although she's starting here soon, the whole thing with COVID has meant I had not met her in person until right now. And so Chung-Pei I've known for quite a number of years now, and Jessica Liu almost as many years, not quite. And Michael I just met, and gosh, a graduate student. It's like, wow. So I really just want to say I feel privileged to be here at Berkeley and to have had the opportunity to work with, to hear from, to help support these remarkable scientists. And that's even better than getting to meet Kip Thorne. So there you go. So I also want to say thank you to our alumni and friends for gathering tonight. I hope these lectures evoke in you the same excitement you felt as a student when you learned about some of the great research that maybe your professors were doing, and maybe you even got to participate in that research, as we hope students here all get the chance to do. We talk a lot about basic science around here, and I thought I'd share with you something I've heard a lot of scientists say. We all, and I include myself in this category, we all think there's going to be some aha moment where we've discovered something remarkable. But in fact, it's not usually like that. Instead, usually you start to see something interesting happening in the observations or in the data or even in the simulation. And you say to yourself, well, that's weird. And in fact, you start looking around then for more and more weird moments until you realize you're onto something. And that is actually what basic science is like. It's much more of a, that's weird, it shouldn't be doing that, than an aha light bulb kind of moment. It's more just puzzlement that you then dig into. It's incremental. It's sometimes very slow. As an experimentalist, I can vouch for you. It is sometimes extremely frustrating when your equipment is broken or when things are not working the way they should. But it's exciting and it's important. And without it and without those weird moments, we won't get to the discovery of a black hole or to vaccines or to cures or to climate solutions. Anyway, so a lot of you have asked about whether or not we will continue these remote programs when we get back to normal, assuming we know what normal is. We are eager to see you in person, but you can rest assured that we will continue to do this remote programming that brings our friends and alumni from afar into our midst. This is one of the things that we've really enjoyed figuring out, is that how well this works, and it's a good complement to some in-person events. Your support and your advocacy for Berkeley means everything to our faculty like Chung-Pei and Raffaella, and to our graduate students like Michael and all the other incredible students, postdocs, and faculty who are here at Berkeley. We're extremely gratified for your continued interest in Berkeley, and which is of course alma mater to so many of you, and to the fantastic work being done here. If there's anything you want to learn more about, or if you'd like to support our work, for which there is a deep need, please do be in touch with us. We absolutely want you to be part of advancing basic science and discovery at Berkeley, and we look forward to the next one of these events. And with that, fiat lux.